Hello and welcome again to my Physics Online video lecture series. In today's video we're going to be discussing the photoelectric effect. This is the second part of the discussion of the photoelectric effect. The first part I just simply presented the experiment, the basic rationale behind how the experiment might be conducted, and gave a rough sketch of what the results of the experiment were. So in today's part, I want to talk a little bit about how we typically interpret those results and therefore what it is that in some sense we discovered. Now, we owe a lot of the interpretation of the photoelectric effect to, of all people, Albert Einstein. This is in fact what won him the Nobel Prize, was his interpretation of the results of the photoelectric effect. It wasn't his work in relativity, however important that may also be. So we can in some sense begin by recalling what all the experimental parameters were and what the results were. Instead of doing a recall slide as such, maybe I'll just pull open the slide from that last video. So this is basically like the summary of results, and for today's video this is kind of like your recall slide. Basically you can change out what the material is, and for any given material, and the materials are metal. We're not talking necessarily about insulators here. This doesn't really work well with rubber, for example, but for metals, you have some minimum frequency which results in there being a current regardless of what you do with the bias voltage and the intensity. You can call that minimum frequency a cutoff frequency. It's usually denoted with an F min or an F0 in it. And as long as the light frequency is above that frequency, you can, in principle, detect some, basically some photocurrent, as long as you don't go too bad on your bias voltage. Obviously, if you have a very strong bias voltage against the direction in which the current should be flowing, then you're going to need quite a bit of photoelectrons in order to generate any current, and they have to be at quite high energy to get through that bias voltage. But for the most part, as long as you are above that cutoff frequency with your light source, you can detect some sort of current. And especially you should be able to, provided that you have no bias voltage or a forward bias voltage. Alright, other than that, the frequency itself doesn't have any effect on the current. So changing the frequency of the light doesn't mean that you get more or less current, as long as you're above that cutoff frequency. On the other hand, changing the brightness of the light does affect the current, again provided that your light frequency is above that cutoff frequency for the material. So if I double my current, if I double my intensity S, then I typically also double my current I, provided that my frequency is sufficiently high, and also provided, of course, that we're not doing something strange with a reverse bias. Okay. Also, if I fall below that minimum frequency, then any amount of brightness short of ionizing the material via tunneling ionization effects tends not to produce any photocurrent. A sufficiently bright laser, you can kind of ablate the material and ionize it via other effects, but these guys did not have access to that level of intensity in these experiments. You need like a really, really high intensity laser to do that. But so long as you're just using like a plain pointer laser or light source, they didn't have lasers at this time, so maybe as long as you're using like just a sort of like bright light source, you will not get any current if your frequency is too low. Finally, you can change out the bias voltage, and essentially what this does is it affects the current if you have a sort of reverse bias. So as long as you have a forward bias, the current more or less stays constant and is determined by the light intensity. And then as long as but if you do a reverse bias, then changing the bias voltage does affect the current, and there is a voltage, reverse voltage above which you don't get any current anymore either for a given light, and that value is determined actually by the frequency of the light. So you have kind of like this interesting tangle of different variables that are coming into play for this particular experiment. So how do we interpret it? Well, the first step of the interpretation is to treat the light as if it is quantized. Now, this is an idea that also comes up in the blackbody radiation interpretation that Planck basically did. He proposed that the energy of the energy was quantized with these radiators, and therefore that the oscillations that could produce these light had specific discrete values somehow, and thus that although the spectrum appears continuous, it also starts falling off above a certain frequency as well. Okay, so Einstein kind of furthers this by saying, suppose that light is quantized. The quantization basically means instead of just thinking of light as here's this wave that's incident on my metal, what if this is really consists of a bunch of individual photons of light, each of which has the same frequency as this wave. So they kind of like carry a frequency information, and that frequency information pertains to the energy of the photon. So photon is, we might call it a particle of light. More properly, it's more thought of as a quantum of light. And the wave then consists of many of these photons in the same way, or in a similar sense, I should say, as, say, an ocean wave consists of many, many, many particles of water moving. Now, the most important part of this, or maybe the most important part of this, is that these photons, they all have the same frequency, and that frequency is tied to their energy. So we could write the equation E is equal to HF, or if you would prefer in terms of the wavelength, this is HC over lambda. So E equals HC over lambda, or E equals HF, is the energy of the photon. Now, a minor aside here that is maybe not so minor actually. This term HC, you can convert units around, but if you've watched my previous video about introducing two constants in a unit, you should know that this has a value very nearly equal to 1240 eV dot nm. So if I have a photon whose wavelength is, let's say, 620 nanometers, that is more or less red light, then our photon energy E, which is hc over lambda, becomes 1240 eV dot nm divided by 620 nanometers. And so this is basically 2.0 or 2.00 eV of energy per photon. This also means, for what it's worth, that we can figure out how many photons are present in a given beam of light, let's say per second. Case in point, a 1 watt source is 1 joule per second. So 1 watt is 1 joule per second. That is 1 joule times a conversion factor of 1 eV per 1.6 times 10 to the minus 19 joules per second. And then we can basically divide that in some sense by how many eV per photon. So divided by 2 eV per photon. And if you do all that, you get how many photons per second. So the number of photons per second, which I'm going to represent as n dot, ends up being about 3.125, without paying attention to significant figures, about 3.125 times 10 to the 18 photons per second in this light beam. Alright, so let's get back to this experiment and our interpretation thereof. Well, how does this energy value, this E equals HF, help us figure out basically all these experimental results? Well, let's say that we have a sort of binding energy for the electron on the surface. Alright, that means we need at least this much energy to knock the electron loose. Now, for a beam in which the intensity is, we'll call it like relatively low, and a 1 watt beam that is focused to an area of a few centimeters is, yes, a very hot beam. You would probably burn yourself if you put your hand under that. You'd certainly feel a lot warmer. It's still a very low intensity beam. There's still few enough photons that you're basically interacting 1 photon at a time with a given electron, and since the electron energies are themselves quantized, the result is that if your energy is below that binding energy for that electron, then you can't knock the electron off the plate or off the metal surface to create the photo current. So the first part of the interpretation, it explains why is it that you have a minimum frequency. You need the frequency to be sufficiently high. This frequency has to be sufficiently high that this energy is greater than the binding energy. Now we call that binding energy the work function of the material. Okay, so this work function is basically telling us how much energy is needed to remove an electron from an atom in the metal. We usually use a phi for the work function. So if E, which is equal to HF, if this is less than phi, then no electrons. Similarly, if the energy of the photon, HF, is equal to the work function, then you can get a photocurrent, provided, of course, that you have some sort of a forward bias voltage that will essentially like give you a field to accelerate the electrons across the gap between your two, your cathode and anode, your two plates. If the photon energy is greater than the work function, then the result is that you will typically expect to see photocurrent even against a bias voltage. Okay, so what does that tell us in turn? Well, we can convert these all into terms of frequencies. In some sense, you can say that phi is equal to h times f minimum. So in some sense, we can say this is the case where f is less than f min. This is the case where f is equal to f min. And this is the case where f is greater than f min. So we're looking at what is the frequency of the light relative to the minimum frequency to knock electrons out of this atom. Alright, so there's a further interpretation going on here though with this last point. You can get a photocurrent even against a bias voltage provided that the bias voltage is not too great. So in some sense you can tune the voltage higher and higher and higher and therefore cause a larger and larger deceleration of my charged particles. So let's say that I have reversed the bias so that my field is in this direction like this, and I now have an electron E minus which I want to move this way. It has some deceleration, so this will, let's write this in black. This basically may have some initial velocity this way, but it has a deceleration. It has an acceleration in the direction opposite its velocity. And so that voltage at which you stop seeing any of these is sometimes called the stopping voltage. So stopping potential is basically the potential energy delta V such that no current is detected anymore. And it's basically a function of your frequency f. And the way that that basically works is E times delta V stop should be equal to K initial, which is basically your 1/2 m electron V initial squared. In some sense, this is my V initial up here. Now, typically we don't use this particular expression to figure out the stopping potential or to tie it into the rest of this discussion. Instead, we note that the total energy of the photon, E, which is equal to hf, must be equal to the kinetic energy initial plus the work function. Okay, and so my stopping potential, this right here, can tie in to this equation here. And so basically by tuning my potential until I no longer find any photocurrent, basically means that I'm actually figuring out the value of my work function for my given photon frequency. So I know the frequency of my light because I know the wavelength. I know that C is equal to lambda f, and that C is equal to a little less than 3 times 10 to the 8 meters per second. So if I know what the wavelength is, then I know what the frequency is, or vice versa. This basically means that I'm able to figure out my kinetic energy via the stopping potential, which in turn means I can solve for this work function. Alright, so going back to those graphs that I showed in the previous video, wherein we use the same intensity light but at different frequencies, and what we find is that there's different values for which we get these stopping potentials. So here's one, here's another. They end up having the same current once the voltage is forward bias. So this side would be forward bias. This one would be reverse bias voltage. And this would be like F2 maybe, this would be like F1. These right here, these points at which we stop seeing current, these would become your stopping potentials. And essentially this is telling me that F2 is greater than F1. I need more potential to stop electrons generated by these photons than by these photons. Now with that said, we should also make note of the fact that these ones right here, we should also make note of the fact that these frequencies are actually known or knowable because we're controlling the light source. We're putting different filters in front of it, for example, or we're swapping out the light source to some other color light source. And so we're controlling the frequencies, and then we're looking for what is this stopping potential. And this stopping potential we're figuring out once we have delta V stop. So in some sense that's those values. E delta V stop is equal to whatever the kinetic energy initial is, but that in turn is equal to HF, H times F, not H sub F, H times F minus the work function. Now it's important enough, again, to put in a box. So again, E times delta V stop is equal to HF minus the work function. Alright, so if I happen to have E, well, I know E is the electron charge, elementary charge of 1.6 times 10 to the minus 19 coulombs. I know that one. So once I found the delta V stop, these intercepts essentially, and I know F, the photon frequency, then I've now figured out what the work function is for my metal. Now the last piece of information that goes with this, the last piece of the interpretation, is what about changing the light intensity? What does that do? And for that, we kind of come back to this discussion that I had that I said at the moment was kind of like an aside. It becomes a little bit more important now because we just said that Hc is 1240 roughly eV.nm. We just said that photons have an energy E hc over lambda or hf, and that gives us the energy per photon in eV. All right? And then we tied that together by saying if I know what the power is of my laser or my light source, whatever, then I know how many photons per second are incident. Now, usually what we measure rather than, or what we have rather than just the power is sort of the intensity, but either one works for this analysis. The intensity just means now we know how many are incident per square centimeter per unit time, and that becomes important because we also know how many electrons there are per square centimeter. And as long as you're below some sort of saturation threshold, which you're below the saturation threshold. If you hit the saturation threshold, other interesting things start happening. If you're below this saturation threshold, normal achievable powers, a flashlight or a very, very bright halogen type light or a handheld laser, something like that, then the more intense you make your source, therefore the more photons are incident per unit time. And therefore, the more you expect to have electrons knocked off of the metal per unit time. And because you have more electrons getting knocked off of the metal per unit time and then moving across this gap and becoming photocurrent, the more the current is. So assuming that you have sufficient energy to knock an electron free, meaning assuming that your frequency is above that cutoff frequency, and assuming that you have no bias voltage or maybe a forward bias voltage to help these electrons make it across the gap to where they're supposed to go, assuming that you have those two things in place, the higher your intensity, the higher your value of photons per second that interact with and knock free an electron. Therefore, the higher the number of electrons, therefore the higher the value of the current. And that matches with this other graph that I showed in the last video, where we basically said, what if we change the intensity of the light and do the scan of the voltage versus the current, keeping the frequency of your light source constant. And it turns out that the higher the intensity, S is your intensity, the more current you get. And so this gives us a complete description of the photoelectric effect, a complete interpretation of these results, which is what we were hoping to get. So that's all for today's video. I know it was a bit long, but hopefully you enjoyed it, and hopefully you understand photoelectric effect a little bit better now. This, in some sense, concludes the main of my discussion of the photoelectric effect. I would recommend the PhET simulation for photoelectric effect if you want to go tinker around some more on your own. And so that's all for today's video. Hopefully you learned something, and thanks for watching.